In this video, I'll be going over the graphs of exponential functions. So, as you can recall, f of x equals b to the x. That's the most basic form of an exponential function, where b is a value that's greater than 0 and also not equal to 1. So here in this bulleted list are some of the characteristics of an exponential graph. So let me just graph a very basic function here. So that's the general form. And I'll just go through each of these bullets. This graph is one-to-one. In other words, it's one way to think about that is it's going to pass the horizontal line test. No matter where I draw a horizontal line, it'll only hit the graph in one location. There's always a horizontal asymptote at y equals 0. So before any transformations occur, that's where our horizontal asymptote is. The domain is all real numbers and the range is 0 to infinity. Because there is a horizontal asymptote at y equals 0, we don't include 0 in the range. There's no x-intercept. There is a y-intercept, always at 1, 0, 1. Okay, and then if b is greater than 1, this will be an increasing function. So this one that I graphed, this has a b value greater than 1. If b is less than 1, and really what it should say is b is between 0 and 1, because what we set up here is b is always greater than 0. So if b is between 0 and 1, we're going to have a decreasing function, and it'll look like this. Okay, and all the other characteristics hold up here. We still have the same intercept, same domain and range, and horizontal asymptote. So looking at this example, sketch a graph of f of x is equal to 0.25 raised to the x. State the domain, range, and asymptote. Okay, so in this one, our b value is equal to 0.25, and that is less than 1 but greater than 0. So this is going to be a decreasing function, and it's still going to cross at 0, 1. We know that that is kind of our first point, 0, 1. In other words, when I input 0, I get 0.25 to the 0, which is equal to 1. If I wanted to find a second point, probably the easiest thing would just be an x value of 1. 0.25 to the first power is 0.25. Okay, so maybe somewhere down here. And then we know that this is a decreasing function, and it has a horizontal asymptote of y equals 0. Okay, so that's what our graph is going to look like. The domain is going to be all real numbers. For every exponential function, the domain is always all real numbers. For the range, this is going to be 0 to infinity, not including 0. And then the horizontal asymptote will be y is equal to 0. Okay, so pretty much every graph that is b to the x power is going to look, we can graph it just like I did here, and it's always going to be one of these shapes with a y-intercept of 1. All right, so the next thing we'll talk about is how we can do transformations for these graphs. And we can apply the 4 transformations that we've seen for other functions. We can shift, reflect, stretch, or compress to the parent function b to the x. And it'll always have this increasing or decreasing shape. So we're going to go through each of the transformations. Graphing a vertical shift, what we do is we add or subtract a real number value outside of the function. So d here is that vertical shift. And we can see these examples here. So g of x is equal to, well, actually, let me start with f of x is equal to 2 raised to the x. This is like the parent function. And I'm putting it in quotes because there's not only one parent function. The parent function is any b value raised to the x. So the parent function here is 2 raised to the x. So if I add 3 to that, that's just going to shift the graph up, and that's how I get g of x. And then if I subtract 3, that's going to shift the graph 3 units down. And so what that impacts is the range and the horizontal asymptote, as well as the y-intercept, right? So if I'm looking at g of x, the y-intercept is shifting up. I have a new horizontal asymptote, and then the range is from 3 to infinity for that graph g of x. So if I was to compare g of x to f of x, well, it's kind of just what I said. For f of x, that's the parent function. For g of x, that's the transformed function. So for f of x, the domain is all real numbers, and that's the same for g of x. As with any exponential function, the domain doesn't change. The horizontal asymptote, we're going to say for f of x is y equals 0. For g of x, I'm shifting that up 3 units. So this is y equals 3. I skipped the range for no reason. But the range corresponds to the horizontal asymptote. So the range for f of x is 0 to infinity. And for g of x, it's 3 to infinity. And then lastly, the y-intercept. The y-intercept for the parent function is 0, 1. For g of x, it's 0, 4. Y-intercept 0, 4. So when we talk about comparing these functions, this is kind of what we want to do. We want to discuss the key features of each graph. All right, so to graph a horizontal shift, we're going to add or subtract a value inside the function. So we're going to add or subtract something to the exponent here. Okay, and we can see that once again, our parent function is f of x, and then we are shifting right 3 units and left 3 units. And remember, if I want to go left, I guess this is right. If I want to go right, I'm going to subtract 3. If I want to go left, I'm going to add 3. Okay, so similar idea, g of x and h of x. Oh, we're not comparing one of these with the parent. Okay, so let's see. So g of x, the y-intercept, well, let's just go through the domain, the range, the y-intercept, and the horizontal asymptote. Okay, so the domain, that's the easy one. It's always all real numbers. Same thing for h of x. Okay, the range, because we have no vertical shift, the range is 0 to infinity for both of these. The y-intercept is a little bit more difficult. So to find the y-intercept for g of x, and to find the y-intercept of any function, we always input 0. So 2 to the 0 plus 3, this gives us 2 to the third, which is 8. So the y-intercept for g of x is 8. This graph isn't like 100% precise, but it's going to be right there. So 0, 8. For h of x, we're going to do h of 0 is equal to 2 to the 0 minus 3. So I get 2 to the negative third, which is 1 over 2 to the third, which is 1/8. So this is 0, 1/8 here. And something like down here. And then the horizontal asymptote for each of these functions is y equals 0. Okay, so that's how we can compare these functions that have a horizontal shift. All right, and now let's graph this function that has both a horizontal shift and a vertical shift, and then we'll find these key features. Now, my suggestion would be to just make a table of values. And we don't need very many values, as long as we just remember what the parent function looks like. So the parent function here is f of x is equal to 2 to the x. That's the parent. Okay, so I guess there's a couple ways we can do this. One, we can just work off of the parent function. The second way would be to make a table of values. And honestly, just looking at the parent function and considering these two transformations is probably going to be the way to go here. So let's hold off on making a table of values on this one. So if we can remember what a parent function looks like, the y-intercept here will give us one of the points, and it's 0, 1. So that's for the parent. And then let me do this a little more organized. So parent, and then 2 to the x minus 1 plus 3. So our parent function is 2 to the x. Okay, so the y-intercept for that one, for the parent function, is 0, 1. For the shifted function, well, what are we doing? We're going right 1, up 3. So to find the y-intercept, well, right 1 is going to change the x-coordinate. So now I'm going to have a 1 for the x-coordinate. And then up 3, if I'm starting at 1, up 3 is going to be 4. So my new y-intercept, or my previous y-intercept, that point, 0, 1, is now shifted to 1, 4. So I know that we are going through that point 1, 4. And I'm calling it y-intercept in quotes because it's not actually the y-intercept for this function. Okay, so that gets us one of the key points. If I want to find the actual y-intercept, well, I'm going to do f of 0 here. So that's 2 to the 0 minus 1 plus 3, which is 2 to the negative 1 plus 3. 2 to the negative first power is 1 over 2 plus 3, which is 3.5 or 7 halves or 3.5, whichever form you like. So 0, 3.5 right here. Okay, well, that doesn't look like it's going to give us very much, but we can also think about what the horizontal asymptote was on the parent function. So the horizontal asymptote for the parent function was y equals 0. On the new function, well, I'm shifting up 3. So my new horizontal asymptote is y equals 3 here. So doing it in a different color, my horizontal asymptote is on this y equals 3. Okay, and then the last thing just to remember is that because this b value is greater than 1, that means this graph is increasing. And that makes sense for what the points I've plotted so far. So the graph is going to look something like that. And again, we don't need to be worried about being 100% precise. The idea is, can we represent all the shifts or the transformations? And then do we have the general shape of this correct? All right, so let's find the key points we want. The domain here, again, all real numbers. The range is from 0, nope, not 0. The smallest y value we hit is 3 to infinity. And then the horizontal asymptote is y is equal to 3. Okay, and one thing to mention is that one of the endpoints of the interval for the range always corresponds to the horizontal asymptote. Okay, couple more transformations to discuss. If we have a stretch for an exponential function, that's when we have a value of a as a coefficient here. So a, the function or the graph of the function will be stretched vertically. So we have a stretch if the absolute value of a is greater than 1. So if I have something like this, how about negative 3 times 2 to the x? So absolute value of negative 3 is 3. That's greater than 1. That's going to be a stretch vertically. And we'll talk more about what that negative does. We're compressed vertically if the a value is less than 1. So f of x, actually, let's do the name of a different function. How about h of x is equal to 1/2 times 2 to the x. Okay, so we see two examples of this. On this first graph, I have an a value of 3 here for the g of x. So we can compare those two graphs. The g of x graph is getting stretched vertically. And what that does is it multiplies. So this 3, what that means is multiply all y values by 3. And that's what we see here. The y-intercept is 1, and then it becomes 3. And one last thing, there is always a y value here, but it's just a 1, so we don't really consider that. And that 1 has no impact. It doesn't stretch or compress the function, the graph of the function. All right, and then the second graph, similarly, I have 1/3 here compared to 1. So what that's doing is multiply each y value on the graph by 1/3. That's the same thing as dividing by 3. So to compare f of x and h of x, so what we want to do is on this second graph over here. So let's just talk through. So the domain, let's do f of x first. Domain, range, y-intercept, and the horizontal asymptote. And then h of x. We're going to have the domain, range, the y-intercept, and the horizontal asymptote. Okay, so for f of x, the domain, that's the easiest question we get asked. The range here for f of x, well, f of x is the non-transformed function. That is always 0 to infinity, and that means the horizontal asymptote is y equals 0. The y-intercept is going to be 1, even though it doesn't quite look like it's exactly at 1. It is at 1 using that the equation for the function. And then h of x, well, the domain, -infinity to infinity. The range here, oh, I guess something's wrong here. Something's wrong with this graph. F of x is equal to 2x. What I notice here is that y-intercept is not at 1. It looks like it's at 2. So that graph is misleading. I'm going to use just the equations here to compare these. So again, that graph is a little bit misleading. I should just say it's incorrect. That y-intercept is wrong there. Look at it over here, and it looks correct down there. So not sure what's going on with this graph. Again, I pulled it from the textbook. So, but anyway, the domain for h of x, which is this red graph, the domain is going to be -infinity to infinity. The range is still 0 to infinity because there's no vertical shift. The y-intercept, well, the y-intercept for the parent function was 0, 1. So the y-intercept for the transformed function is 1/3 of that y-intercept. So it's 0, 1/3. 1/3 times 1 is 1/3. And then the horizontal asymptote, again, because there is no vertical shift, the horizontal asymptote does not change. Okay, and then we have one last transformation to discuss, and that is a reflection. So we can have two types of reflections. We can have an x-axis or a vertical reflection or a horizontal reflection. So for the vertical reflection or the reflection across the x-axis, we have the negative outside the function. And then and that's what's getting represented here. And then if it's a negative inside the function, we have the reflection across the y-axis. So let's compare f of x to g of x, and we'll do that over here. So f of x, g of x. Okay, so we've already seen this. The domain is all real numbers. The range is 0 to infinity. The y-intercept is 0, 1, and the horizontal asymptote is y equals 0. So for g of x, the thing that's changing is the range here and the y-intercept. So the domain stays the same. The range now is -infinity to 0. The y-intercept, well, before the y-intercept was 0, 1. And what's happening is when we have this negative here, Actually, sorry, we're doing this one. When we have that negative there, what that's doing is each y value is multiplied by -1. That's what that negative does. So if our original y-intercept was 0, 1, now it's 0, -1. Let me write that a little more clearly. Okay, and then the horizontal asymptote, same horizontal asymptote, y is equal to 0. Okay, and then lastly, here's a summary of all the transformations for an exponential function in the form f of x equals b to the x.